an infinitesimal increment of proper time, and this is the path length along some trajectory. Implicit in this is all the things so you have to come to this in order to make sense out of this. Well, there's two things we want to do. First, I want to rewrite this in the terms of what is a tensor mathematics, meaning I want to go back into the installing this with the full tensor notation with the bases vectors and see how this comes about. We should do that. But also, you need to be able to quickly understand how these two components here, right? This is how these two components here relate to the path itself. And implied in this, of course, is that there's a path in space-time, right? x1, x0, and as we've always said before, because it's a manifold and we're talking about a path, which is a curve, we can parameterize it. We'll parameterize it with tau. And there's the function, it's x mu of tau, evaluated at tau equals 0 is the beginning of the path, and then the end of the path, or at least the end that we're going to consider for the problem, is x mu of tau at tau equals 1, and then if tau goes from 0 to 1. It doesn't matter what tau goes to. This is just some arbitrary gap. But tau will be the proper time. So that's what x is. And implied, that's what these x's are, right? These x's are the coordinate values, x0, x1, x0 of tau, x1 of tau, x2 of tau, and x3 of tau. Those are the coordinates, and these are differentials. So we're thinking this in special relativity ways when we present it. So we actually think of these as differentials. Calculus is differentials. The connection between those and the true forms, right? The tensor notation that we had before. So we'll get to that. But this expression tells us the path length in space-time, and this is the space-time of special relativity. So we know that eta alpha beta equals minus 1, 1, 1, and 1, right? I guess 8, 0, 0, 0, 1, 1, 2, 2, and 3, 3, right? So clearly we have d tau equals minus dt squared, minus dt squared plus dx1 squared plus dx2 squared plus dx3 squared. And of course the minus sign here, that can be traced to the fact that in this metric, right, using the mostly plus metric, time-like paths, or the paths of material particles, will always end up being negative. And we're defining proper time, which we want to count off in positive ways. So we have that negative sign there to give us the proper time to be positive. And we're using the mostly minus convention. So anyway, so that tells us that proper time is going to actually be this integral from 0 to 1 of d tau. That's the proper time interval that it takes this particle to traverse this line, which is what we call it's really the length of the line. Because remember, tau in our units where c equals 1, it's going to literally be a length. It's going to be measured in meters. And to convert back to seconds, of course, you would divide by whatever your favorite units of c are. So this integral represents the amount of proper time or the path length in special relativity. So now let's try to break that into something that's actually a bit more mathematical. Let's consider abstract before we can. Before we can actually jump into the math. Just so I can explain to you what's at stake here for that very first step. Imagine that there's some black hole. Maybe it's the black hole of our galaxy, what is it, Sagittarius A star or something. I can't remember the name, but there's this black hole that's in our galaxy, which is not an active galactic galaxy nuclei, right? It's an inactive one, so there's these stars orbiting it. So this would be, say, the plane of the orbit of one of the stars, and this star starts here, and it kind of orbits. Maybe it has a very little something like that. And then maybe there's even another one that's really far away. Comes like this and goes around, and presumably it bends back around and keeps looping up. It's just very fun. So there's a bunch of stars in a space-time diagram going around the galaxy. Now notice, I'm trying to start by not thinking about this in terms of your regular picture, where you have here's the black hole, and here's one orbit, maybe that would be the star, and then here's the orbit of the blue star, and then maybe the orbit of the green star, or something like this. Right? Just thinking of it, if all of those orbits were in the same plane. So the first thing is this is not an accurate representation of what's going on in the center of our galaxy, except that there are stars going to be orbiting a supermassive black hole, but they're not all in the same. They're not all doing orbit in the same plane, of course. They're doing orbits in all kinds of different wacky planes. But if they were doing it all in the same plane, then we could compress the picture into a plane and then put our time axis here. And this is the picture we would get. The point is that our little guy in the elevator might start here. Well, let's say he starts here, right? And he has some strange state of motion, but let's just say he gets sort of captured by this first star. So he's kind of in orbit around this first star. But maybe he wanders a little too close to this star and ends up in orbit around that star, and then kind of somehow swings through this whole thing, and maybe even gets ejected from the whole process. That is possible, I think. I think when you're dealing with multi-bodies in orbits around each other, you can actually get ejected from the system one way or another. And I'm sure that's even extra true in the presence of a supermassive black hole. But the point is that while this guy's doing it, right, while our little man in the lab, the astronaut in the lab, is free falling, this is a totally free fall condition, right? The only thing that's happening is he's just following a space-time trajectory according to geodesics. These are geodesics, which we're actually going to be beginning to touch on today. If this astronaut is just freely falling, there's nothing this astronaut can do to figure out that this is the path that he's on, as long as he only relies on measurements inside his little laboratory. This whole process is totally invisible to him. And you might, when I first learned about this, I was thinking, wait a minute, what about inertial guidance systems? For airplanes, inertial guidance systems, and things of that nature. And if you don't remember, inertial guidance system would be equivalent to a device that's essentially a mass. There's a very sort of solid, fixed mounted object that's fixed to your aircraft or your spaceship, and then there's a spring, and then there's a mass. And of course, if you accelerate in this direction, the spring will get compressed, right? So you'd say, well, look, here you are here, and you're falling into the star. So clearly you're accelerating. Look, your space-time path is changing all over the place. So there's all kinds of acceleration. So this compression can can be measured and we can track it. We can actually figure out that you're accelerating in these weird ways, and from that acceleration, we can extrapolate your velocity. We can calculate velocity. We can, you have 3 of these, one in each direction, and you can actually reproduce this trajectory. But the problem is that inertial guidance systems don't work in free fall, right? Inertial guidance systems only work when we're talking about non-gravitational forces, right? And that's because ultimately this mass is subject to the exact same gravitational field conditions that the laboratory itself is, and therefore it's not going to compress the string. You should understand this, by the way. If you don't understand why an inertial guidance system will not work in free fall, then a truly inertial guidance system, one that's designed something that can be modeled vaguely in the way I described here with a mass and a spring, then you're a little bit behind for where you should be for this. This is an important principle that, it's basically a statement of the Einstein equivalence principle, right? Because if it's true that we can find a reference frame that is total special relativity, then that means it's in uniform motion, right? It's in uniform motion, and these things will never make any demonstration of uniform motion. So if that frame exists, then of course an inertial guidance system won't work. Okay, but anyway, so we have this free-falling observer in this gravitational field, and now we know that regardless of what coordinate system we have, this guy will always be able to establish a coordinate system, or what they're experiencing, because they're free-falling, they're experiencing the coordinate system, the anti-coordinate system of special relativity. And likewise, the path length of this path is the proper time that is ticked off on the clock that's sitting with this observer. So this guy, he's got his clock, his little cesium clock, the atom with its register. That little clock ticks, and you can actually plot even amounts of proper time ticked off here. And there will be time for he may be moving faster and slower, right? Like he may be moving a little slower out here, away from the star, but then as he gets to the star, he's moving faster. So the ticks, would be slow and then speed up, and here they can be really fast. Well, here you actually have some kind of time dilation, right, where the ticks go, but the amount of space, right, in this point you would actually have time dilation. The ticks and the amount of space are actually under the influence of the theory of general relativity itself. And it'll be fun when we get to a chance, we'll be actually be able to study this. We'll be actually be able to see that the proper time ticks off at a very different rate at different places near this supermassive black hole. Anyway, but the length of this, calculated exactly, so the length of this line, however, is not subject to the rule that we just learned. But the path length, this d tau minus eta alpha beta dx alpha dx beta, that's for special relativity. In this path is clearly subject to all kinds of gravitational forces, and we're talking supermassive black hole. We know the general theory is what applies here, and now we have to think a little bit differently. We still get the benefit of the proper time, right? We're still going to calculate the proper time, but now it's going to equal the metric of the space-time, dx alpha dx beta. And this metric of the space-time is to calculate this path length. It's the whole darn space-time, right? It's this coordinate system, the coordinate system that is used to capture the coordinate time and the space. And that is, this guy is a function of space-time. This represents the path just as before. X alpha is a function of tau. That is this path. But remember, this metric can only be made to be inertial at any given point in space-time, right? At any individual point. But along this whole path, it won't be. So you're going to have to do this full integral to capture the time of the path of this particle. And furthermore, to complicate this thing even more, this is for a material particle, right? A material particle, which means that d tau, it means that it's time-like, it's a time-like path, right? So at every point in its traversal, or in its motion, it's always a time-like interval. And because of that, this interval makes sense, 0 to 1 d tau. But if it was light, if we were talking about now the trajectory of a light ray, say some light ray which would be moving very fast relative to light, so it would be something like this, maybe it would be just bent a little bit by the supermassive black hole, that particular trajectory. That always will be 0, right? That's always going to be have a path length of 0 when calculated using this method. So that makes it very difficult. First of all, you can't calculate a proper time for light for that very reason. But we try to split the situations up when we talk about geodesics, time-like and null geodesics in one. But right now what you have to remember is that in general relativity, the path length is calculated using the full metric, and in special relativity, it's calculated using the Minkowski metric. And that's because the Minkowski metric is the metric of special relativity, right? In special relativity, everywhere in space has this metric. But in general relativity, only every point could. There is a coordinate system where every point could be given this metric, but only at the point. If you could find a transformation of a coordinate system such that the entire space-time had this metric, then you're basically working in a special relativity condition. The space-time would be flat. That's actually what we mean by flat. Flat space-time means that everywhere that's true. Right? Curved space mean time, that's impossible. It's impossible to make that true everywhere. Okay, so now we're going to take this and now we're going to squeeze it into some very interesting mathematical modeling that will give us ultimately some really important information about how particles move in space-time. Just based on one thing only. Just based on the Einstein equivalence principle that at any given point we can make this true. Folks, let me show you first, by the way, how eta alpha beta dx alpha dx beta, how we make contact between our understanding of, here we have just the component of the metric tensor, let's get the flat space metric tensor, how do we make contact with eta alpha beta dx alpha tensor product dx beta, which is an object that takes two vectors and returns a real number. We have to do this. So first we notice this is a real number, right? So that's good. And here we're interpreting these as differentials, and here we're interpreting these as covectors, or alternatively one forms. And this is a tensor product instead of just some regular real number multiplication. So how do we, how does this jive? And the answer, of course, is we need two vectors to feed into this to get something that we can interpret like that, right? As we feed in two vectors, we'll get a real number. So that real number better be interpretable like this, in this form here. So imagine one point in space-time and another point in space-time, and then you can imagine the tangent or a vector connecting the two, right? Vector connecting the two. Now this has to be really small, but if it is really small, we can call that vector, say delta, let me see, how about I call it delta x is the name of the component, partial alpha like that, right? This is the vector basis in coordinate representation, and this will be a component, so it's delta x alpha. Okay, so in the past we would have written, say, x alpha, partial alpha, to be an arbitrary vector in the coordinate basis. This time I'm going to x, I'm going to call it delta x to give it suggestively. Okay, so that would be like a little vector that would extend from one point in space-time to another. Now the problem, of course, is I've emphasized that that's really not, these vectors live, this thing lives in a tangent space here, right? If it goes from point A to point B, there's a tangent space, and this vector lives inside this tangent space. But the units can still be right, and it will still, the idea is that it will still give us, if this is the coordinates of the point A, and this is the coordinates of the point B, you can definitely imagine that x mu of the point A plus these delta x mu's will equal x mu of the point B if B is close enough to A. So as B gets close enough to A, this logic is just fine. And even though this vector literally lives inside this tangent space, right, when these things get so close together, you can actually allow yourself to imagine this as a vector extending from A to B. And if you do that, you put in, what would you do? You put in delta x of, not beta, I guess we have to do something else, delta x gamma partial gamma, and delta x epsilon partial epsilon, like that. So you're putting in a vector to the plus, right? And then you crunch the tensor product, and you end up with delta x gamma, delta x epsilon, and eta alpha beta, and then you get these things. You get dx alpha partial acting on gamma, and you get dx beta acting on epsilon, which of course these are just delta functions, alpha, gamma, delta, beta, epsilon. So what you end up with is eta alpha beta, delta x alpha, delta x beta, and then of course you continue to push the notation further where these delta x's become infinitesimally small, and now you recover the differentials of calculus. So you understand, this is still the same thing, right? We're talking about a little interval, but here we create that little interval inside a tangent space that should be what it takes to create this coordinate addition in the appropriate way. And then we just run we just crunch the tensor product machine on those two vectors, and we basically get this object, which in its infinitesimal form is completely implausibly linked to this object. And everything's going to run the way it's supposed to. Okay, so that works obviously for flat space. This is for any zero tensor. This exact analogy will work. So that's the connection between our work and the classical notation. So we won't deal with it this way for the purposes of this, because this is how most of the books you're going to be reading and following along with deal with it. So we begin by understanding that in this little sealed lab that's just freely falling in some space-time, then we know that we can establish a coordinate system where a test particle in this lab, say the test particle system red thing, moves in a straight line. And we know that because the Einstein equivalence principle says so. Right? That's a stipulation of the theory. It's an axiom, right? I guess an axiom is a little bit more of a mathematical term. It's a postulate. It's a basic premise of the theory. It only comes from insight, right? If there's no development of it, Einstein famously just said it was the happiest thought of his life because he wrote it down, thought about it, and the general theory of relativity in many ways flows forth from it. But let's see how. So we're going to call the straight line motion of this particle in space-time. We're going to give those coordinates a name. We used to call them x in that previous site, but here we're going to call them, let's see, what's this Greek letter? We'll use the Greek letter psi, right? Something like that. How would I do with psi? I think it kind of looks like an E, actually. Let me work on that. Hold on. It'll look like this. And that will be the coordinate system that we're dealing with that is inertial, right? It's inertial. It's a freely falling coordinate system that exists because of the stipulation of the Einstein equivalent principle. And in that thing called falling coordinate system, we have straight line motion, which implies that d of psi, let's see, sorry, the second derivative, the second derivative of psi alpha with respect to the proper time equals 0. Right? So the proper time, of course, is remember this is a path that's parameterized by the proper time. So the second derivative of this path with respect to the proper time of the particle is going to be 0 because this motion is straight line motion. And straight line motion of special relativity. And of course, again, this is all inside this local frame that's as small as necessary for this to be true. Now, the proper time, right, is still the case because it's within the psi frame that we're dealing with alpha, beta, and then it's going to be this differential of psi alpha, the differential psi. But I'm not saying psi, I'm saying psi, right? Just get that right. Differential. So this is still true. This is the special relativity condition, right? So we assert that, and we've now invoked the Einstein equivalence principle at this point. So our next step is to say, well, let's reduce a coordinate system mu, and x could be any coordinate system at all. There's no coordinate system that we're really unrestricted. It can be perfectly curved, it can be rotating and spinning, it can be accelerated motion is fine. It doesn't really matter. All that has to matter is that the freely falling coordinates, right? So any given point. So here's our psi coordinates, right? Say psi 0 and psi 1. I'm supposed to have a little thing with that. And then here's our other coordinates, right? And I'll call that one x0 and x1. And obviously there's 2 and 3 for both of these. But one thing that is going to be clear, or that has to be the case for what we're working with, is that psi 0 is a function of x0, x1, x2, and x3, which I can write as psi 0 is a function of x right? Something I could also write this as, I'm just trying to do this every way you might see it, x alpha. So, each of the alphas are increment. It's a function of the other coordinates, right? Likewise, xi1 is a function of x0, x1, x2, and x3. So this is perfectly sensible, of course. This is our coordinate transformation. These are our transition functions from what is a manifold, right? That's what these are. These are the transition functions. But this point here, it's got coordinates in x, and it's got coordinates in y, and the coordinates in y is some function of the coordinates in x. Presumably, if you know the coordinates of this point in the x system, you'll be able to calculate it in the psi system. And likewise, you have one of these for psi2 and psi3. These are the transition functions. So now, using the chain rule, we start with our expression that we know to be true because of the Einstein equivalence principle. Right, we start with that, and we invoke all of the four functions. This is a way to write in one fell swoop, basically, all of these, right? We just write it down as e psi alpha of x, right? So knowing that this is the case, knowing that this exists, and we have this other coordinate system, how can we work with this equation? What do we do next? Well, we, of course, invoke the chain rule, and this becomes d by d tau of partial derivative psi alpha with respect to x, I guess what we will call it is x mu, and then partial derivative of x mu d tau, like that. Right? And then we execute the next derivative, right? We execute this derivative, and we are now using the essentially the chain rule, and this is an alpha, right? And that chain rule will give us, let's see, partial derivative partial derivative of psi alpha d x mu, and then then it's actually going to be, it is going to be squared, but then it's going to be d, because it's going to be dx mu, and then dx mu d tau. That's going to be the first term, and then it's times the second term, so it's dx mu d tau, and then it's plus, and that'll be d psi alpha dx mu, and then it's just the second, I think it's just the second derivative, dx mu d squared, or dx mu it's dx mu, dx mu squared d tau squared, So then you get this expression, right? That expression equals 0. So what we've basically done is we have just taken this derivative, but using this expression, we now have we have a function, right? We have this function here, the function of the size, as functions of x. Remember, because each psi alpha is a function of x. So this derivative makes perfect sense. And of course, dx mu d tau now is we would have to have the path of this particle in the new coordinate system as a function of the proper time, right? So as long as we can have that, we're fine. We can take all of these derivatives, and when we do, this simple expression in the flat coordinates, that's a statement that's very trivial in the flat coordinates located at this particular point P, or this particular point inside our spaceship, which is in free fall coordinates. Right? That equation of motion in the free fall coordinates becomes a bit more complicated in the more general coordinate system. In fact, let me write this out a little bit more clearly. We're going to get partial squared e alpha dx mu dx nu multiplied by partial x mu d tau and partial x mu d partial tau plus partial psi alpha partial x mu second partial x mu tau squared equals 0. And this function of the x's through e alpha of x, right? The transition functions. And likewise, there should be an x mu e alpha, right? Or x mu psi alpha. I can say e for psi because it kind of looks that way. But and then these guys depend on us knowing the path in space-time with a function with relative to the proper time. Otherwise, you can't calculate those derivatives, right? So we end up with this expression. Now, to move on from this, we want to simplify this a little bit using an interesting fact. Okay, so we will take this expression that I just wrote and we're going to simplify. We're going to try to simplify. And what we're going to do is we're going to multiply both sides of the equation by the partial of x lambda, partial of psi alpha. We're going to multiply the whole thing by this expression. So to do that, I'll put that here, copy, paste, here, right there in the middle. So we're going to do that. I've got to move this over. And then this, I should do that a little more in my work, because it actually looks pretty good. I'm going to just erase this little mess. So I'm going to put it in both of those places, and of course on 0 it just goes away. Now, what's important about this is that I can look at this term here, this times this, right? And I'm basically dealing with something that looks like, I want to look at this one. This is the one I want to look at. Right, that's much cleaner. I don't have to, I'm trying to peel apart a second derivative there. That's not what I was after. So looking at this one, this expression actually equals delta mu lambda. Now convince yourself of that, right? You should spend a little time convincing yourself that that's the case. It's always, all these things are always these chain rule things. So you know the partial alpha, or partial psi alpha, respect to partial psi alpha, you know that is certainly going to equal 1. to rewrite everything again. And I'll start by working over here. I'll start with, let's see, partial squared x mu, partial tau squared. But because the mu is converted to a lambda by this delta function, I will turn that mu into a lambda. And then from that, I have to now work with this expression. Right, so this expression, if you kind of look at it now, so what we have these two derivatives here that are kind of the same, and we have this more complex term up front. So let's see if we can figure this thing out. So I'll just put in these two terms first, partial x mu, partial tau, and partial x nu, partial tau. I'm switching the mu to the new order, which is not a big deal. And then I have this term up front, which there's nothing we can really do about it. It's just sort of a big mess. Let's see if I take this. Hold on, let me first erase this delta function. I guess I'll put the delta function here, mu lambda. And then I'll take this and move it here so I have enough room. And then I will draw partial x lambda, partial epsilon alpha d squared psi. I call it epsilon, I call it psi, psi. And partial x mu, partial x nu. Right, so now I have this guy. So having a look at that guy, and then equals 0. And having a look at that guy, we get into the index structure just for him. We see that we have this summation, right? We have a lower index and an upper index. Right? Because you got to remember, if you have an upper index in the denominator, the big like a lower index, you have a summation there. And then you have this lambda mu nu with an upper index and two lower indexes. So we can actually rewrite this thing in a very suggestive way. It's lambda mu nu, partial x mu, partial tau, partial x mu, partial tau, and partial squared x lambda, partial tau squared plus. And this is our final expression where I made the obvious equal renaming of that complex set of derivatives into this form. Now let's look at this complex set of derivatives, right? This here, the x is a function of psi. Well, that's just an inversion, right, of the alpha as a function of x lambda. You invert that, you have x lambda as a function of psi alpha, right? So you can take that derivative, and then this derivative is just the second derivative of the function we talked about at the beginning, which is basically this function, right? That the inertial coordinates of the lab, and the arbitrary coordinates of the lab, you can take those second derivatives, right? So this object here, this thing here, is based on the second derivative of these coordinate changes multiplied by a first derivative of the inverse of the change. But either way, these functions are pretty well known. These derivatives are established. You're assuming the coordinate systems aren't totally insane, so that all these derivatives should be smooth and exist, which, by the way, is a requirement for a differentiable manifold, right, which is what space-time is modeled on. So now we're actually leaning on our second assumption about this, which is that space-time is a differentiable manifold. So these derivatives are fine. And now we end up with this equation. And this is an equation. This is a differential equation where the independent variable is tau, and the dependent variable is x lambda. This is a lambda, right? So the answer to this thing is x lambda of tau, right? So it is the path of the particle in space-time, right, in the arbitrary coordinate system as a function of the proper time of the particle. That's what this expression will tell you. So there, in this expression, for those of you who've seen this before, I'm kind of thinking that most of you have seen this before, because if you're trying to learn general relativity for the first time, like in this class, it's probably not the right place to be. Right? This is definitely sort of a second pass kind of class. However, the bottom line is this is the geodesic equation. And this guy from our previous lecture about what is a tensor, that is the connection, right? This is the connection. This is the connection. And we have a zero here doing it this way. Now, where did we start? So this is a derivation of the geodesic equation. And where did we start? We started with the presumption of the Einstein equivalence principle, right? Without the Einstein equivalence principle, we cannot say that this freely falling observer, this guy's freely falling, right? And in this freely falling frame, this particle's path is completely straight. So let's actually build that up. Right? So here's the freely falling laboratory. Inside this thing is flat space-time according to the psi coordinate system. And here's the particle, right? Here's the particle. Now, this space-time, as I showed in this sequence, where is that? Way back here. I showed this freely falling frame is doing all kinds of crazy stuff in the universe because it's freely falling under all the influence of gravity, right? So standing out there by that star, watching this thing fall, we see this frame move all kinds of weird ways, right? And that's what the frame's doing. But if you're a guy inside the frame and you're falling, right? And you see this little ball, and it's moving like this, right? That's its motion with respect to you. Meaning, it's like you're an astronaut in a space shuttle and you have a little ball and you're watching it move in front of you. Well, when this frame moves to this position, let's see, hold on. I will do this the obvious way. Hold on. I'm trying to get these cut and paste things down much better. So now when this frame has moved to, say, this position here, right? By that time, this ball moved to, say, that position here. From the perspective of this guy, in the side frame, the ball's moved in a perfectly straight line, right? And that perfectly straight path is epsilon alpha of tau, right? So when we started our equations, when we started our work back here, that's what this was, right? That is the straight path as seen in the epsilon coordinate system, which is moving with the falling line frame, right? So that's epsilon. But the other question is in this frame, this guy who's moving with the stars, in some other coordinate, this person's got the x coordinate system, right? What does he see this ball doing? Well, he sees this ball doing this kind of thing where, well, if it was, let's see, I guess, right, so let's figure that out. If it was totally motionless, it would sort of follow this black line. So it would go like that. That's how he would see the ball go if it was motionless. Like that's the path he sees the head of this observer on. But because there is some motion, this thing drags down just a little bit, right? So it ends up here, right? And then, So the point is that it sees a much more complicated path of that ball. That complicated path is x mu of tau. That's this path here. And the relationship, to figure out what this path is, right? That's the interesting path. To figure out what that path is, I have to solve this equation. And notice all of the relationships between the two coordinate systems, all the relationship between this coordinate system and this coordinate system, it's all buried in this guy, which we're going to call the connection. And we remember the connection from our previous work represented how to understand parallelism in a coordinate system. So this inertial, this rule of, so ultimately, this whole thing leans on the equivalence principle because we stipulated that this epsilon must exist, right? And it exists, it's free falling, so it follows that little lab frame. And this is an arbitrary coordinate system, and the manifold assumption, it gives us what these derivatives are. It tells us these derivatives exist. The manifold assumption tells us we can lay down the coordinates, and that we can create these derivatives. And thus we end up with this equation. And so ultimately, well, what is that equation? What is that equation? How do you tackle that equation? Well, we're certainly not going to do it in this lecture. I'm trying to keep these lectures a little bit shorter than before, than the previous sets of them. But if I was to take this thing out, we can this is a series of equations. Partial x0, partial tau squared, plus, this is x0, gamma 0, mu, partial x, mu, partial tau, partial x, mu, partial tau, equals 0. Now this is the same, right? So there's 4 of these guys, right? So there are 4 of these. Right, so I can actually do this. I can paste one there. I can paste another. And I can paste another. Right? And then all I have to do is erase the zeros and make it a 1, 2, and a 3. And erase that 0.